It says 2:15, so I guess we'll go ahead and get started. Hopefully everybody is here for the Rigid team meeting, right? Okay, good deal. First, my name is Charles Wienrank. I'm with the Illinois Department of Transportation and the Bureau of Research, and I'm on the NRRA Rigid team. And our first presenter this afternoon is Manik Barman. He's with the University of Minnesota Duluth. He's going to tell us about the evaluation of the benefits from structural fibers and thin concrete pavements. And we've done a lot of structural fiber concrete on our concrete overlays in Illinois, so I'm very interested in hearing what Manik has to say. Please welcome Manik.
Thank you, Charles. Thanks, Charles, and everybody for coming here. All right. So, as Charles already mentioned, the title of the presentation is Evaluation of the Benefits from Structural Fibers in Thin Concrete Pavements. Okay, so now since it's a big room, so what I have this pointer, and then I'm just testing, like, Barman, do you hear me back from back?
Yes.
All right, I'll be walking around. Is it okay?
Yeah, you're good. Yeah, very.
Okay, because that's kind of what I'm used to. All right, but if anybody doesn't listen to me properly, I'll go back to it. Okay, thank you. All right, so so at UMD we are involved with a couple of research projects, both are kind of related to the fiber reinforced concrete. Okay, so one project we started in 2016, and Maria is the PL, Tom is also there, team, and many others.
Because we are recording it.
Oh, yeah.
And you, I think we're probably gonna have to use it over there with the mother.
Sure.
We have to anchor you.
Sure. Okay, no, that's a good. Yeah, I forgot for us. Isn't okay. All right. So the research team at UMD, we had graduate students, and these are the names like who actually worked with me in this project, in the couple of projects. Bryce Hansen, Jared, and Uma Arefali. He's a postdoc right now. And then also I really like to thank all those experts people. Some of them are in the TAP members of the couple of research projects, and then also some people who actually contributed in that. Okay, so I see here team, Tom, and many other people here. Also some people who are not in here today, so I really would like to thank Madzel, really helped a lot. Maria is helping. All right, and then Bernard is here. Okay, so all right, so as the title says, like, we are using structural fiber in thin concrete pavement or in overlay. Okay, so when we talk about the thin concrete pavement or the pavement on grade, it's like we are saying that the pavement directly constructed over an unstabilized base layer. And then when you talk about the overlays, there can be different types of overlays. Okay, overlays on asphalt, on composite, or over concrete. Okay, so and then when we say thin, so we are talking the thickness is kind of 3 to 6 inches, or maybe you can argue 6.5, bonded and unbonded. Okay, so fiber reinforced concrete is used for both. Okay, and what are the distressors we see? Different cracks. Okay, so the picture at the top, it's like an old picture from the MinDOT. And then the picture, the other two pictures you are seeing, like these are from recently constructed those main road NRRA sections. I think cell 705 and 805. We can see joint faulting. Okay, so joint faulting also occurs on thin concrete overlays or pavement. Also slab migrations. Okay, so this is one particular district. Actually, Illinois has seen this kind of slab migrations. Look, I think I got this picture from Randy who was telling that this kind of thing happens, but if they use fiber, they probably could reduce. And then I was discussing it with Charles, and he agreed with me yesterday. So when you talk about fibers, there are varieties of fibers, in terms of the material, steel fibers or synthetic fibers, okay? And then varieties of fibers have been used in many states of this country, okay? And then and then if we look at the benefits, what kind of benefits we get out of those fibers, okay? So it reduces the crack, let's say first, like crack initiations. The fibers sometimes helps in that, but the main contributions probably holding the cracks tight. Then it increases the load transfer efficiency. We'll see like how we have some test results, we have some field test results which shows that fiber improves the joint performance or load transfer efficiency. Slab migration we saw in the last picture, reduces the slab thickness or can increase the slab size. I do not know yet, but if you use the BCOAME design procedure or SCPA design procedure, you can see if you use fibers, then thickness can be reduced in the design. So that's there, but the concept of the design or the contribution of the fibers in those design procedure is taken like if we use fibers, we actually artificially increase the modulus of rupture of the concrete. Now if you increase the modulus of rupture of the concrete, you can get a lower thickness. That's kind of the theory inside those design procedures, but that may not be the proper contributions of the fiber, and you will agree with me today probably after these presentations. All right, so the very last picture here at the bottom, this is the picture. I like the picture, like this is this very thin, ultra thin overlay that has been constructed in main road last year. So as Tom said, this one was construction truck, probably came right after the construction or something, but yesterday also I saw, and then I took this picture yesterday. It's like pieces are together. So in our study, like as I said, like we are working on two different projects. One is ending. So in the first one, initially what we did, or also in the second one, we did ask people from different states to provide us some data on the fiber reinforced concrete overlays. We asked how they perform, what kind of fiber they have used, what doses they have used. So I didn't write many other states in here, but this is something like I thought, okay, I will just make one slide in here, and then so that you can also read. So here you can see, or these are kind of states responded also properly with numbers. So here, if you look at a few things I put inside the blocks, so you can see like in this we have like 50 different projects, and out of 50 projects you see only 6 projects were constructed with steel fibers, and others were like 6%, okay, 6% were steel fibers and 94 with structural synthetic. Then we also asked that like what doses that you use, okay, and most of them responded 3 pounds per cubic yard. And then we also probably had an answer like how the doses was selected. We probably did not get a kind of conclusive answer, but answer like, okay, the other state used 3 pounds, that's what we have also used 3 pounds per cubic yard, something like that. Some responded according to the residual strength ratio criteria. So we actually have used fibers, and then we see a lot of pictures they are performing, but actually we really do not know if the 3 pound per cubic yard is really optimum dose or not. So we investigated a little bit on that too. Okay, and these are some pictures like sent to us, or we collected from different published reports or papers. These pictures like from Illinois, the top picture Randy Relish sent to us, also we got it in that report. It says like, this pavement is performing over its design life, even though it probably has some heavy track going over it. So this really performing well. And then we got some pictures where they have not used fibers, and then so this kind of slab migrations. In Main Road, cell 96, it was, I have seen it still performing. In yesterday I saw that, and then right now actually it has a layer of seal coat over it, and Tom said it's because of the safety design, and also they provided that. The joints got deteriorated, but still it is offering the service. Okay, so it was having fibers, too many fibers. Okay, so that's a good thing. So fibers are really contributing. So this is a picture I got from South Carolina. Okay, so the gentleman says that, so this crack here you see in here, so this is, it's a 4-inch thick concrete overlay, 3 feet by 3 feet panels, and he mentioned that this overlay also got crack really in early period of its life, but the pavement is still performing. They constructed it in 1999, right? We'll be going to 2019 next year, so it's pretty 19-20 years this pavement is performing. And then he told that the fiber is probably keeping the pieces together. So they cracked, kind of shattered surface is serving for 17 years. So fibers helping. We got this picture from John. I think you probably said this one. I did not put it in inverted comma because I probably changed a little bit, not the fact but the presentations perspective wise I changed something like that. So you said fibers did not reduce the panel cracking but did reduce crack widths and joint degradations. No faulting was observed on this project. So we have evidences. We have evidence the fiber is, and this slide shows kind of like what different states says. Illinois says this reduced slab migration, joint separation, okay, faulting. Kansas saw like less faulting. Then they say the fiber doesn't fall too much because fiber holds the pieces. In Minnesota, we'll see some graphs again. The increased load transfer. And then Missouri restricted folding, reduced crack width. South Carolina said increased service life. Virginia says fibers exhibited good resiliency in minimizing cracking and crack width. All right, now we know that fibers are contributing. That's kind of the fact I will say right now. And then we have also seen that people use 3 pounds per cubic yard of fibers. Okay, now is it good? Not good. Can we look a little bit in a kind of engineering way or a mechanistic way to optimize the quantity of the fiber, or what fiber is good? What particular properties should be we should be looking at? Okay, and then if we know that, the next questions: how do you quantify fibers benefit and appropriately incorporate them into the structural design? As I said, right now in the structural design, we artificially increase the modulus of rupture. And you will agree with me, modulus of rupture is not always increased by using the fibers. Okay, you will see that. So the design procedure that we are having right now is kind of artificial as far as fiber reinforced concrete is. So, and then we have really good amount of performance data right now, like in different parts of the country. There are plenty of laboratory research data available at University of Pittsburgh. Jeff Rosler has a lot of data. Amanda has data. We currently produce a lot of laboratory data. And then of course Main Road is great resource with all types of data, you know. So since 1997 they have collected data on fiber reinforced concrete pavements. And then of course numerical models. So all those things actually available, and then we probably need little bit of more effort, and then actually this thing can actually go into the design procedure. So this is kind of current status. So now what we have little bit, so I covered a little bit of literatures and what we are actually doing. So in laboratory study, this is just like an introduction picture. So we reviewed like what other people are using, what are the parameters of the fibers they are looking at. Okay, so we saw like a typical volume fraction. Yes, this is also in the laboratory study, field and laboratory study. So people use from 0.25 to 1.5% volume fraction. When I say volume fraction, it's like weight of the concrete, percentage of fibers, volume of the fibers with respect to the volume of the concrete. So if we add, a lot of literature says if we add fibers, of course the slam goes down, okay, and then fiber bowling can occur. So these are kind of the range, typical volume fraction, what people have been used, suggested in the laboratory study or applications. Okay, so and in steel fibers, even though it was not used in too many states, a few examples are there in Illinois. Steel fibers help sometimes in increasing the compressive strength. Okay, you can see here the compressive strength increases, but if you have too much, eventually it doesn't, because the concrete's compressive strength, and if you know only a few particular fibers are in the vertical direction or horizontal directions, a lot of things are on the mechanical orientations too. Sometimes we screwed up if we pour too much of fibers. Flexural strength also, if we add steel fibers, it can be increased. Okay, people say 50%. There is a one study here, I referred, so 50% they said they can increase. Now since this country likes synthetic fibers, so I'm focusing more on synthetic fibers. Now in steel fibers we saw we can increase the modulus of rupture or the compressive strength, but if we use synthetic fibers, really we do not do. We cannot increase. We cannot even increase the modulus of rupture. Now give a pause and think for 5 seconds. The current design procedure that we are having, we are saying that let's increase the modulus of rupture by 20%. But we are using synthetic fiber that does not increase the modulus of rupture at all. So we need to look at it. So here is the thing which is important. So fibers, synthetic fibers or steel fibers, how it performs. So these three graphs, one shows the C shows for that no fiber, and then we have 0.5% volume fraction synthetic fiber, and then 0.5% volume fraction steel fibers. Steel fibers performs better than the synthetic fiber. Okay, but actually we do not use because probably heavy, okay, construction issues, okay, and moreover if we use synthetic fibers, the intended performance, the required performance probably is good enough. Synthetic fibers can serve our need. So this is the contribution, not the modulus of rupture or compressive strength. You see here we can increase the residual strength. So we did a study, a laboratory study, where we had 11 different fibers. One was steel. You see here, I'm missing one here, 10. So I just did not include the trefoil here because I just wanted to focus today on the synthetic fiber. So you here we have 10, but I have deleted the steel one. So here you see, so as you increase the percentage of the volume, the residual strength ratio increases. Okay, so the another thing, actually we can also get residual strength ratio, which is we popularly call it, and then probably all of us are familiar with that. So if we run this kind of test, which is called STM1609 test, so under this test what happens, we apply load, displacement control load, okay, and then we get a peak load, and then because of the fiber, the load does not go down to zero, rather than it sustains some load. So we measure the load at 120 mils displacement, okay, and then divided it by the peak load, we get residual strength ratio. All right, so that's increases with the fiber, not the modulus of rupture. So we developed some correlations. Okay, we probably, if we are like forward looking, and then we want to include fibers into the design procedure, probably these kind of information will be helpful. So you've generated different correlations with fiber volumes, okay, with the The most important thing, I guess, like out of all the slides that I have shown, this is the most important one. So with 10 different synthetic fibers, we had varieties of fibers. Some are straight, some are creamed, embossed, twisted, low stiffness, high stiffness. So among those, you see here, so if you use embossed, okay, if you used sorry, I do not. So here, so if we used embossed or little bit of stiffer fibers, okay, so we get, you see, we get more residual strength ratio with less quantity of the fiber versus this one. If we use straight synthetic, here you see 50% fibers, we have to add more in order to get 20% residual strength ratio. So yesterday when Brett was presenting, we saw like the mixture design for the main road cells, like in order to get 30% of the 30% residual strength ratio, how much fiber we had to add. Okay, so if we had different types of fibers, we probably didn't need that much of fiber. Okay, so this is one important thing. Then we have conducted the load transfer test. So in this test, what we do is, this is a beam, okay? So we apply load on one side of the beam and then measure the displacement on the both side of the beam. It's a dynamic test, okay? These are some different pictures and then it looks like this, you know? So this can give the load transfer efficiency. It's a laboratory method, okay? And then if we run this test, we get some profile like this, okay? So the very first one you see at the crack with 16 mils and then 47 mils and 126 mils. You can see as you go in the right direction, you can see the displacement under the loaded side increases or the displacement under the unloaded side drops when load transfer efficiency decreases, right? So these test procedures can give us these kind of results. Also, a lot of other results we can find out. I'm not spending time on that. So what I wanted to tell you, this is a good procedures to find out the load transfer efficiency of the concrete, okay? And if we use fibers, you see here the very top one shows for no fibers, then 0.25 volume fraction and then 0.5 volume fraction. So and then you can see the difference. We correlated this with the slab test results in University of Pittsburgh. We had done this kind of test on the slab and then we correlated. So you see the round circles, hollow circles are for slab and the other one for the beam. So this is a good method to test the residual strength ratio. So we performed this test on here I think 5 different types of fibers. Again we selected S means straight synthetic, straight twisted, straight creamed, straight embossed. I'm sorry, S is for synthetic, sorry. And then straight twist. So we included different types of fibers. Okay, and then in terms of the load transfer efficiency we saw, okay, so with respect to crack width, the fiber that we used was kind of, it didn't give too much of a difference, but that's the important thing. Sometimes load transfer efficiency can be misleading. Here you see one particular type of fiber, the straight synthetic one, did give more displacement. Even though load transfer efficiency was good, that means if we apply the load, both the slab goes down, load transfer efficiency good, but they goes down more. That's not good, right? So we'll have to be really selective and we'll have to choose good fibers. So we've extended these results to find out. In general, you see here this curve is for plain concrete, then 0.25 and then 0.5. So if we use fibers, well, how much load transfer, additional load transfer we can get from this correlation. So here this is the relation for the displacement, loaded side displacement. So if we want to use fiber and then if the DOT or the agency decides, okay, we probably look for 20% additional load transfer or 30% maybe. So we can look this kind of correlation and then find out how much, what doses we are, what kind of dose we want. One important thing here, in fiber concrete, thin concrete overlays, we do not provide dowel bars. Sometimes do, but most of the time we don't. So when you talk load transfer, it is very important to mention at what crack width you are testing. Why? Because in conventional concrete, you have dowel bars, and dowel bars load transfer sensitivity with respect to crack width is not that much, but for this one it is. So when we are talking about load transfer about the fiber reinforced concrete, we should also look at what crack width we are talking. If we are comparing two joints and they are like the crack width are different, then we are not comparing apple to apple. So we actually developed this kind of nomograph. Okay, so in this one you can see like if you know probably Jeff Rosler's like their study, they are more focused on residual strength, and if so, you know for a particular road section you are looking at 175 or 150 residual strength. So how much fibers you want to use, okay, what type of fiber you want to use, you can get. And if Minnesota duty says no, not only that, we also impose a criteria like we want to get this much percentage of load transfer efficiency for that crack width. So this kind of nomogram is helpful. So all those results that I am showing here, actually this can be helpful in evaluating the contribution of the structural fiber. One more important thing we noticed in here is this: fibers are good, synthetic fibers are good, but there is something called stress relaxation. So if the crack width increases, fibers get some plastic deformation. So coming summer, when the crack width becomes narrow, fiber doesn't contribute if they are not stressed. So that's kind of the thing we should also be looking at. So here you see, so this was a plain concrete. Basically what we did, we widened the crack width and we pushed back. Now when we are pushing back, we saw kind of something similar, but here you see when you are pushing back the crack width in terms of the fiber, so you know the load transfer drops. Alright, so few slides from the field, not a lot of slides. So those are some laboratory studies. There are other laboratory studies available too. So here field study. So I think like Brett has done a great job introducing all those in his presentation yesterday. So all those cells that were constructed with different fibers, composition, different slab thickness, different slab sizes. Okay, so I'm just like looking at these last three boxes. So hopefully we'll be able to get some good results, and then we can move forward. How can we take the effect of fibers in fatigue modeling, faulting modeling, or we can also see how we can modify the panel size or increase the panel size. Okay, so we had different tasks, and the task one was literature review. So we have completed, the report is available online. So other tasks basically looking at performance analysis and then work towards developing some procedures so that we can use in the future design procedure. So Ben has given me some data on those active main road cells, new one. You see in here, the very left one is the control. So we saw like we did not see a great amount of load transfer increase, but 10% in general, irrespective of the fiber doses, okay? But you see the consistencies in the fiber cells kind of consistent. So there are like in these 4 lines. So there, the first 3 are 3 different joints, and the last one was average. So when we looked at when we separated that at approach slab and lead slab, you can see on the control side there is one with 59% LTE. We also analyzed those data for the loaded side displacement. Okay, so here you can see inconsistency. Okay, but I don't know for any reason cell number 606 Oh yeah, cell number 606 was 1 inch thicker. That tells me the reason now. It was 1 inch thicker so that it did not get too much of displacement and that explains. I was looking for an explanation. Alright, so you see the consistency in here. If we use fibers, so something is, now if I compare this with different crack width or different time, then we will get more information. This is an old picture here is showing the temperature versus load transfer. You can see the for the fiber one is kind of consistent. The crack width changes. This is some results actually. I think like I'll be really glad if we can get these kind of results for those new sections, because when we will consider the fiber's contribution of the design procedure, the fatigue consumption of the overlay will be different in different season, and then if we know the crack width, we can really use them in the faulting model. So if we get something like that, that will be really great. So the concluding remarks, we know structural fibers are contributing and we know that we have the evidence. You see the synthetic fibers are mostly used. We saw straight fibers are not great as compared to the others. And then fibers can improve the load transfer efficiency, right? Say I was 20%, but we'll have to see more results from the main door sections. Now at the end, I'll just say like these are the benefit, not the modulus of rupture. So probably, so I hope like this NRA project that we are doing here, actually, this will give a chance to consider the contribution of the fibers like more mechanistically or more appropriately. So I'm looking forward to this project, then hopefully we can get something. Okay, so these are some pictures I got it from Tom. So I remember once Matt Zeller told me, you know, if a pavement cells get distress in the main road is kind of blessing. It's not. So we already got some cracks. Now we'll have to see like if fiber can help them, maintaining these thing, or we get wider crack or something. So we'll have to see. Okay. So I'm open to any questions. So if you have any question. Yes, sir.
I have a question. Some of your early slides, you said that the curation at the joint was basically because there were too many fibers in the joint.
Yeah.
Was this because you had to add additional water to the mix to get workability, or what was going on, freeze-line damage, or what was causing this issue?
Okay, I think I will answer to that question, but the expert is in here. Okay, Tom can definitely tell a better answer than me. So what I suspect, so that particular cell was having 25 pound per cubic yard of fiber. Remember, we are talking about 3 pound per cubic yard versus 25. So that too much of fibers mostly probably occupied the space of the aggregates, which basically participate in the load transfer. That's one thing, but I would say like other kind of, you know, so I think like spalling because of the fibers spalled, you know, instead of like it hold the pieces together. Imagine like a bunch of fibers like at one place. It doesn't have aggregate, or it doesn't have like mortar paste around it, right? So I believe that kind of thing, but if you have a better answer than this.
Yeah, it's only deteriorating at the joints.
Okay, but you didn't have to add any more additional water, use water reducers and so on compared to control mix? Because that was always a concern of this, using fibers, is that we'd have to raise the permeability of the mix by adding additional water to replace them.
We'd have
That
to
was
go
always
back.
the issue.
Yeah, we had to
deal
go back.
with this thing.
This was the 3M initiative.
Yeah.
We just went with our recommendations, throw it all in, you know.
Yeah, Cliff came and talked to us in the early 80s, Cliff got him at 3M.
We did add more water, add more water to it to make it more flowable.
Yeah, well, that's the negative side of it,
Right.
because then you're just creating another monster. And there's a balancing point.
Yeah. But I think like if we add fibers up to like 8 or 10 pound a cubic yard, we will not see that kind of things. That was for 25 pound per cubic yard.
Can I give you some insight? That early
Sure.
3M fiber was a monolithic, right? I worked
Polyolefins.
for- yeah.
Mono.
So polyolefins are very hydrophobic. What happens when you stick water on them? Actually, they beat up. There's no
Yeah.
interface bond in those
Yeah.
fibers.
Very good.
Where does all the water get into the panel? At the edge. So every one of those fibers became a fast path for the fusion of water
Yes.
into the concrete, and big shock that you might have spalled it right off.
It's very appropriate answer.
So, you don't have enough time for all the questions I have.
Yeah, sure.
So what would you like? I mean, you got all this stuff that you guys are playing with, and this is a pretty old space, right? Fibers and concrete in the materials world is not what I'd call a super active research space. I mean, you mentioned you really like something that maybe is more elastomeric, right? The problem with all these synthetic fibers is they've been stretched to the edge of their elastic behavior.
Yeah,
You grab those and stretch them just a little bit more, and they'll fail brittlely.
yeah, I agree with you, and that is the reason I put that carb, and then that's what you are probably talking about. So I completely agree. So we'll have to take care of this one when we're
There aren't any elastomers on the market today that are polymeric fibers. They're all polypropylene stretched to its alignment. These polymer chains are so highly aligned now that you just do the littlest bit more strain to them and they just snap, right?
Yeah.
So the whole functional mechanism here is just tortuous pull-out.
Yes, but what I'm just telling you is, even though it does, but I think still like, 50, 60 mils or even 70 mils, if you stretch it up to that much, then actually you're still not like you are having a plastic deformation. You can still have some contributions. You might not be having like 30% load increase, but you still have. But if all the joints are not deployed and all of a sudden one crack is like ½ inch wide, then that joint needs a full depth replacement, I think.
So my question would be, you've mentioned as if these ultra low modulus plastics, because they're 2 orders of magnitude lower in modulus than the concrete around them. I think the aggregate angularity is probably a piece of measurement that you didn't share about the vertical fault, that the plastic's not going to hold it. It's only going to hold it this way. That's the crack determination. That's why these things were designed for slab on grade industrial floors, right?
Yeah.
That don't go through freeze-thaw cycles.
Yeah.
So I mean, if you tell us more about the angularity of your aggregate, I don't know that I wouldn't not use them, but I might design my system to be a little bit more characteristic, that I get more orientational alignment of the aggregate, so that that's handing the folding.
Yeah, sure. Yeah, I think like, Bernard, do I have a point?
Let me just chip in something.
Yeah.
One more quick comment, then we have to move on.
Sorry?
So just one more quick comment, and we can move on.
Yeah, okay. It just, these are very valid concerns. However, we have to look again at the mechanism of load transfer. There are still three parts to load transfer: the base, mechanical load transfer, and aggregate interlock. Fibers are expected to enhance aggregate interlock by keeping the aggregates together.
Yeah.
Let's not forget that.
Yeah.
It doesn't behave like a dowel. It still helps the aggregate interlock. I just wanted to chip in.
Yeah, no, actually, I think like he explained it. So that's the thing, like if we are not solely dependent on the fibers. I think that's it, I guess.
Yep.
All right, thank you.